Voyager, humanity's eternal journey beyond the Sun. The story of the Voyager mission begins with the limits of our understanding of the cosmos. The entire odyssey can be traced back to the insight of Gary Flandreau, a scientist at NASA's Jet Propulsion Laboratory, who in the 1960s realized through pencil and paper calculations that the outer planets would align in a rare configuration occurring only once every 176 years. This cosmic arrangement of Jupiter, Saturn, Uranus, and Neptune provided a chance to use gravitational slingshots, allowing a spacecraft to leapfrog from one planet to another while gaining speed and drastically cutting travel time. Instead of taking 3 decades to reach Neptune, a probe could get there in just 12 years. Recognizing the fleeting nature of this opportunity, NASA quickly set plans into motion. And by the summer of 1977, 2 nearly identical probes, Voyager 1 and Voyager 2, were launched just 15 days apart. Though their mission was originally limited to reconnaissance of Jupiter and Saturn, what followed would become one of the greatest achievements in the history of space exploration. During their initial encounters, the Voyagers exceeded all expectations. Voyager 1, after its flybys of Jupiter and Saturn, revealed breathtaking details of the gas giant's turbulent atmospheres, powerful magnetic fields, and diverse moons. Among its most stunning discoveries was the detection of active volcanoes on Jupiter's moon Io, the first observation of volcanic activity beyond Earth, and the recognition that Saturn's largest moon, Titan, possessed a thick atmosphere even denser than Earth's, raising tantalizing questions about its potential for complex chemistry. Meanwhile, Voyager 2 embarked on a slightly different path, allowing it to complete humanity's only close-up encounters with Uranus in 1986 and Neptune in 1989. These distant worlds, once thought to be quiet and frozen, revealed themselves to be dynamic and surprising. Uranus displayed a bizarrely tilted magnetic field and an unexpectedly active atmosphere, while Neptune shocked scientists with ferocious winds, the fastest in the solar system, and a mysterious storm system akin to Jupiter's Great Red Spot. Voyager 2's passage through the outer solar system proved that even the most remote planets were alive with weather, magnetism, and geological activity, shattering long-held assumptions about the nature of these distant bodies. The original planetary tour concluded in the 1980s, but the Voyagers were far from finished. NASA extended their mission to pursue an even more audacious goal, a journey beyond the protective bubble of the Sun's influence into the realm of the interstellar medium. As the probes pushed outward, they studied the solar wind, magnetic fields, and cosmic rays, transmitting their findings to Earth through the Deep Space Network's massive 12-meter-wide radio dishes. Despite operating at the speed of light, signals faced increasing delays, now requiring more than 20 hours for a round trip. Data were stored on old-fashioned 8-track tape recorders before being beamed back, a reminder of just how dated their technology is. Yet, this very design, robust and deliberately engineered for reliability, proved remarkably enduring. Roughly the size of a Volkswagen Beetle, the spacecraft functioned autonomously, guided by primitive but resilient software, backup systems, and a design philosophy that emphasized redundancy. Even the asteroid belt, once feared to be a dangerous gauntlet of debris, was successfully navigated by both probes, demonstrating the soundness of NASA's engineering. As the Voyagers pressed farther into deep space, they provided humanity's first direct look at the heliosphere, the vast bubble dominated by the Sun's solar wind and magnetic field. Its outer edge, known as the heliopause, marks the true beginning of interstellar space, where the influence of the Sun yields to that of distant stars and galactic forces. 4 years, scientists waited eagerly for signs that the probes had crossed this frontier. Voyager 1 reached it on August 25, 2012, at about 121 astronomical units from Earth. Though the crossing was not as obvious as expected, rather than an abrupt shift in magnetic field direction, the spacecraft recorded a dramatic increase in plasma density, evidence that the solar wind no longer dominated the surrounding environment. The magnetic field orientation, however, remained puzzlingly consistent, suggesting that the transition was far more complex and turbulent than once believed. 6 years later, on November 5, 2018, Voyager 2 also crossed the boundary, confirming the earlier findings and validating that both spacecraft had truly left the Sun's sphere of influence. These momentous passages marked the first time humanity had physically entered interstellar space, providing data about a region once thought unreachable. Beyond the heliopause lies the theoretical Oort cloud, a vast spherical shell of icy bodies believed to surround the solar system and supply long-period comets. It will take tens of thousands of years for either Voyager to even approach this region, but their trajectories will eventually carry them onward toward the stars. Voyager 1 is headed toward the constellation Auriga and is expected to pass within 1.6 light-years of the star Gliese 445 in about 40,000 years, while Voyager 2 drifts toward Sagittarius, destined for a similarly distant stellar encounter. Long after their signals fade, these silent emissaries will continue their lonely voyages, carrying with them humanity's first messages to the galaxy. Sustaining the Voyagers for so long has required ingenuity and constant adaptation. Their power comes from plutonium-238 radioisotope thermoelectric generators, which gradually produce less energy each year. To conserve dwindling resources, NASA engineers have had to shut down non-essential instruments, carefully deciding which scientific tools to keep active and which to let go. These choices are never easy, but they are guided by the mission's goal of stretching operations into the early 2030s. Engineers have reprogrammed software remotely, rerouted circuitry, and devised clever workarounds to extend the spacecraft's life. Each byte of data received is precious, hard-won, and immensely valuable, offering unparalleled insights into cosmic rays, plasma waves, and magnetic interactions in the interstellar medium. What was once purely theoretical, our models of how the heliosphere interacts with the broader galaxy, has now been directly measured thanks to these twin probes. Among the most surprising findings after crossing into interstellar space was the magnetic field's persistence. Scientists expected a dramatic reorientation but instead found continuity, indicating that the heliopause is not a sharp edge but a complex, diffuse boundary where the sun's influence gradually diminishes. The measurements of plasma density were particularly groundbreaking, offering the first direct confirmation of interstellar plasma and proving beyond doubt that the Voyagers had entered a realm shaped not by our star but by the collective influence of countless others. Each discovery has refined our understanding of how our solar system fits into the Milky Way,